Dear ladies and gentlemen, your attention is offered a report on the topic Comparative Analysis and Model in Safe Variability Areas of Power for the VVER-1000 and AP-1000 power units. My name is Sergii Saukh. I am Doctor of Science, Professor, Correspondent Member of the National Academy of Sciences of Ukraine. This overview discusses the challenges and opportunities associated with the integrating renewable energy sources and nuclear power into modern energy systems. It covers topics such as the operation flexibility of nuclear power units like VVER-1000 and AP-1000 methodologies for modeling power system dynamics and the mathematical descriptions of nuclear power units in the energy system models that prioritize higher levels of the renewable energy supply and demand while transitioning towards a more sustainable and resilient energy infrastructure. The penetration of large volumes of uncontrollable electricity generation from renewable energy sources, from solar radiation and wind, leads to the need to use controlled electricity generation in the power system in volumes sufficient to balance demand and supply. The presented graphs of the residual daily electricity consumption in the summer and winter of 2021 actual data and 2050 forecast data show a significant increase in demand for the maneuverable power of nuclear power units, provided that the share of renewable energy source increases from 7% to 30% respectively. The question arises, with such a perspective of power system capacity development, will it be possible to balance their load modes with existing and promising nuclear power units VVER-1000 and AP-1000 respectively? The power change parameters of the VVER-1000 provided in the technological regulations are justified in the project and regulated based on the requirements of safe operation of the reactor and the conditions of operation of the power unit in the basic mode and an almost constant level of thermal power. At the same time, the design of the VVER-1000 reactor provides for a list of modes that are currently not used in the operation of the nuclear power plant power units and are not included in the list of permitted modes in the technological regulations for safe operation, but can potentially be considered acceptable for implementation under the conditions of experimental confirmation. Comparative analysis of the AP-1000 and VVER-1000 shows a more flexible algorithm of AP-1000 operation in daily power regulation, which can be described by the scheme 18-2-2-2 instead of 12-3-6-3 for the VVER-1000 during 19% of the fuel campaign, and the actual absence of reactions on the need to ensure the dwell time over the entire range of reactor power changes. Comparison of design characteristics of VVER-1000 and AP-1000 power units are presented here. Usually, the load regimes of nuclear power units are determined by a priori determined load schedulers, which significantly limit the adequacy of the representation of the maneuvering properties of such power units in power system models. We offer a mathematical description of the areas of safe loading and power maneuvering of nuclear reactors for an adequate representation of their maneuvering capabilities. Let us denote the relative power N and present its rate of change in the form of a function f, which depends on the value of N. We will present relation 2 in the form of a differential equation 3 with distributed variables n and t. We will write the latter in the integral form 4, which will be used later. We will present the tabular characteristics of the power variability of nuclear power units in the form of the step function 5. Substitute this function into the previously obtained integral equation 3 and obtained algebraic equation 7, in which the f functions marked with the capital letter are the original functions of the f function marked with the small letter. Solving equation 4, 8 with respect to delta n for various values of n and with fixed time intervals delta t, namely 10 minutes and 1 hour, yields characteristic depicting the maximum rate of increasing in thermal power of VVER-1000 and AP-1000 power unit reactors from its current value. These characteristics are presented here. The characteristics obtained reflect the power unit's capabilities to operate safely during maneuvering modes. The areas of safe maneuvering with the power of the AP-1000 power unit are much wider in a comparatively larger range of its loads. It is essential to incorporate conditions of safe loading and power maneuvering for the VVER-1000 and AP-1000 power units into dispatching models and electric power systems and planning tasks for their development. We define the following conditions for the AP-1000 power unit. They are presented here in the form of a system of restrictions, both on the amount of power and on its decrease or increase during the time period delta t. The mathematical description of the area of safe maneuvering by the power of VVER-1000 power unit is more complex. The upper limit of the rate of increase in power is a piecewise linear function depending on the temperature delta T. Here, the alpha and beta coefficients are used. The calculated values of this coefficient are presented in the following two tables for time steps of 1 hour and 10 minutes, respectively. The resulting systems of constraints serve mathematical models representing safe maneuvering areas of AP-1000 and VVER VVER-1000 power units. These models are specifically designed to accurately capture the characteristics of safe maneuvering regarding the power output of both existing and promising nuclear power units. They are intended to be utilized in tasks related to planning the development of electric power systems with significant shares of electricity production generated by wind and solar power plants. Thank you for attention.